And welcome back. As we go ahead and continue our journey through astronomy, we're going to go ahead and segue into looking at the behavior of light and how that's going to affect our cosmic journey. So when we start talking about the behavior of light, one of the things we need to know and why we need to know about light is because a lot of times we want to know about these celestial objects that we see in the sky. Now, the nearest star to us is so far away that the fastest spacecraft that we have would take almost 100,000 years for us to get there. Yet, we want to know what material this neighboring star is composed of and how it might differ from our own sun. So, if it's so far away, how can we learn about the chemical makeup of this star or any other neighboring stars? Well, in astronomy, one of the things that is a unique challenge is that most of the objects that we study are completely beyond our reach. For example, the temperature of the sun is so high that any spacecraft that we have that would try to go visit it would be fried long before it actually reached the sun itself. And the stars that we want to see further out are so far away that a visit to those stars in our lifetimes would be not possible with the technology that we have available. Even light itself, which travels at a speed of 300,000 kilometers per second, takes more than 4 years to reach us from the nearest star. And that's the fastest thing that we know in the universe. So if we want to learn more about the sun and other stars, we instead have to analyze them from a distance. So let's start off by first looking at the sun. Now, if you look at this photograph of the sun, it may not be something that we kind of expect. We look, oh, the sun is usually this big yellowish orb in the sky, and this very clearly isn't. Well, that's because this picture was actually taken at several different wavelengths of ultraviolet light, and the color code reveals activity in our sun's atmosphere that we cannot observe with normal visible light. This is why it's also very important to observe the sun and other astronomical objects in wavelengths other than just the visible band of the light spectrum. And this particular photo, as I've already mentioned, was actually taken by a satellite above the Earth's atmosphere because the atmosphere actually absorbs much of that ultraviolet light that comes in from space. So, let's learn about some celestial objects here. One of the things that we know about these celestial objects is that coded into light itself and other kinds of radiation that reach us from objects in the universe is actually a wide range of information about what those objects are like and how they work. If we can then decipher this code and read the messages that are contained within it, we can actually learn an enormous amount about the cosmos. The visible light and other radiation that we receive from stars and planets is actually generated by a process all the way down at the atomic level. Therefore, if we really want to appreciate the grand cosmos and all the design that goes into it and how light's generated, we actually have to kind of almost take a more granular look and explore how these atoms are actually working and interacting with the cosmos at large. So, in fact, there's actually almost a bit of irony that we have to understand the very smallest things to really understand the largest structure of the universe, because those smallest things are going to really kind of dictate a lot of what we need to know. So let's start off first by looking at light and radiation itself. One of the key ideas is that visible light is not unique. So what we see with our normal range of colors and stuff is actually just a familiar example of a much larger family of radiation. Now, the word radiation that we use is going to be used pretty frequently here in this lesson, so it's important to understand what we are referring to when we're referring to radiation. Now, in everyday language, radiation is often used to describe certain types of energetic subatomic particles released by radioactive materials in our environment. So we start associating things with like cancer and stuff like that. But when we look at this in astronomy, radiation is a much more generalized term that's used for waves, including light waves, that simply just radiate outward from a source. So when we're saying something has radiation, it means it's emitting waves of some kind from a source. Now that's going to tie into our next thing, which is of course gravity, magnetism, and light. How are these all related? Well, Newton's theory of gravity accounts for the motions of the planets as well as objects on Earth. Now, if you were to take Newton's theory and apply it to a variety of different problems, you'll actually find that this same kind of thing dominated the work of scientists for nearly 2 centuries, because they were trying to problem solve. They're trying to put something together to really figure out how the cosmos worked. In the 19th century, many physicists actually then turned to the study of electricity and magnetism, which are also intimately connected with the production of light. And one of the pioneers of this was James Maxwell. This is a scientist who played a huge role in the field, very comparable to Newton's role in the study of gravity. And James Clerk Maxwell was born and educated in Scotland, and he inspired by several different ingenious experiments that showed very intimate relationship between both electricity and also magnetism. And so Maxwell said, I think there's a relationship here. So he actually developed a very coherent theory that described both the properties of electricity and of magnetism. And his theory is actually what's going to give us to the insights into the nature and behavior of light. So what exactly was Maxwell's theory of electromagnetism? Well, we start looking at what it actually is kind of asking us to believe. We first need to understand that the typical atom consists of several types of particles, several which not only have mass, but have an additional property called electric charge. Now, in the nucleus of every atom, of course, are protons, which have a positive charge, and outside our nucleus are electrons, which have a negative charge. Now, Maxwell's theory deals with these two electrical charges and their kind of effects on the environment around them, especially when they are moving. Now, near an electron charge, another charge feels like a force of attraction or repulsion. Opposite charges attract, and like charges will repel. You've probably heard opposites attract, and like repel. You probably have heard that terminology before, but this is where it is coming from. And so, with magnetism, this was actually a property that had been well known for most of recorded human history, but the cause of magnetism was actually not understood until the 19th century when people like Maxwell came along and actually started putting forth theories as to how it worked. Experiments with electrical charges actually demonstrated that magnetism was simply just a result of moving charged particles. Sometimes the motion of these particles is very clear to us, such as the coils of heavy wire that make an industrial electromagnet. We can very clearly see how that electromagnet is generating a field of magnetism. Now, other times it's much more subtle. In many of the ways the electrons inside the atoms are actually spinning in roughly the same direction, it's the alignment of that motion, that spinning, that causes the material within to become magnetic. Now, magnetism has a role that it plays with other forces. Physicists particularly use the word field to describe the action of forces that one object exerts on other distant objects. So, for example, we say the sun produces a gravitational field that controls Earth's orbit, even though the sun and Earth do not come directly into contact with one another. Now, using this terminology, this concept of a field, we can say that stationary electric charges produce electric fields, and moving electric charges also produces electric fields. And this relationship that we have between electric and magnetic phenomena is even more profound if you really start to think about it. In fact, scientists have done experiments that showed changing magnetic fields could produce electric currents, and because we can produce those electric currents, those changing electric currents could in turn produce magnetic fields. So it's a very interrelated property here. So electric and magnetic field changes and it could continue to trigger each other. So anytime you start making these electrical changes, there might be changes in magnetism. So James Maxwell, of course, we already talked about him. He did some analysis of all this. And he's like, well, what would happen if the electric charges were oscillating? In other words, they moved constantly back and forth, going from one to the other and back and forth. And he actually found that the resulting pattern of electric and magnetic fields would actually spread out and travel rapidly through space. And as we shall see, atoms and molecules actually tend to oscillate back and forth all the time. And that oscillation actually gives a resulting kind of electromagnetic disturbance. And these little disturbances are actually one of the most common phenomena that we can observe in the universe. And that's going to lead us into our next topic, which is that of waves. Now, you might think at first that there are very few situations in nature where an electric charge might oscillate, but of course, so something similar happens when a raindrop strikes the surface of water or a frog would jump into a pond. We get these ripples that come out from the source. Now, this disturbance moves outward and creates a pattern we call a wave in the water. Now, of course, this is water that we can very clearly see and observe, but this, of course, can happen in other mediums. And the medium that we're going to look at this through is electromagnetic radiation. Maxwell was able to actually calculate the speed at which an electromagnetic disturbance moves through space. He found that's equal to the speed of light, which already had at that point been measured experimentally. And on the basis of that, he's kind of speculated that, well, light was simply just one form of a family of possible electromagnetic disturbances that we now call electromagnetic radiation. So, for example, when light enters your eye, its changing electric and magnetic fields actually stimulate your nerve endings, which then transmit information back to your brain about these changing fields of information. So all the different things that you're seeing are actually just changes in electrical signals that are allowing your brain to interpret those. Now, the science of astronomy is primarily about analyzing radiation from distant objects to really understand what they are and how they work. So that, of course, is getting us to this wave-like characteristic that light has. The changing electric and magnetic fields in light are much like the waves that can be set up in a pool of water. In both cases here, the disturbance travels rapidly outward from the point of origin and can use its energy to disturb other things that are farther away. The waves generated by charged particles differ from water waves in some profound ways, however. Water waves, of course, require water to travel in. Now, sound, for example, is another thing that can have waves. And in this case, it's typically a pressure disturbance that requires air to travel through. But with electromagnetic waves, they don't require water. They don't require air. In fact, they don't really require anything at all. The fields that are generated with electromagnetic radiation can move through a vacuum. In other words, outer space. That's why even though there's all this kind of empty spot between the sun and us, we are still getting that light, all that radiation that's coming from the sun because it doesn't need a medium to transmit through. So these electromagnetic waves was a pretty cool thing, but it was also very disturbing in the 19th century to scientists because they're like, wait a minute, there has to be something that fills space because what we know of waves, what we have observed is that it has a medium that has to go through. So like, well, light has to travel through something because we observe that it has these wave-like properties. So they came up with something called the aether. Well, the aether was simply just the substance that they said it must inhabit space. Well, today we know in space there's no such thing as an aether, and that electromagnetic waves simply just have no trouble moving through empty space. They don't need a medium to transmit through. The other difference between electromagnetic waves and other traditional waves is that they move out at the same speed in empty space, which is, of course, the speed of light, which, of course, happens to be the fastest possible speed in the universe. It doesn't matter whether those are visible light waves, those are gamma rays, whatever they all travel with the same speed. And no matter where electromagnetic waves are generated from, and no matter what other properties they might have, when they are moving and not interacting with matter, again, they move at the speed of light. Yet, we might know from our own everyday experience that there are different kinds of light. You might have either heard about them, or we might have inferred some from just our lesson here today. And we can actually perceive light waves different from one another in a property we call color. That's simply just within our visible spectrum. So that's going to allow us to examine some properties of waves. So whether it is the up and down motion of a water wave or the changing electric and magnetic fields in a wave of light, the pattern of disturbance repeats in a cyclical way. Any wave motion can be characterized by a series of crests and troughs. So if you look at our diagram here, you can see the crest, of course, is the highest point of the wave, and the trough is the lowest point. And we call a wavelength this point that goes from the crest of one length here to the crest of another. You could also measure a wavelength from the trough of one to the other. Moving from one crest, of course, to the next crest, or trough to trough, is going to complete a cycle. Now, the horizontal length covered by one cycle is called the wavelength. And we typically measure from the crest because that's the high point. And so when we measure from the crest to the next crest, that's going to give us our wavelength. Now, what does that mean? What does a wavelength mean other than just how much distance is between these? What implications does that have for us and light? Well, if we start talking about the wavelengths of light, electromagnetic radiation has, of course, as we established, wave-like characteristics. Now, the wavelength is the distance between crests, and the frequency is the number of cycles per second, and the speed is the distance the wave covers during a specified period of time. For visible light, the regular things that we are used to seeing, our eyes perceive different wavelengths as different colors. Red, for example, is the longest visible wavelength, and violet would be the shortest. Other invisible forms of electromagnetic radiation also have different forms of wavelengths. That's going to lead us into our next thing. So we talked, of course, already about wavelength, but what about frequency? This is something else that you might know about different properties of waves. Well, we can characterize different waves by their frequency, which is the number of wave cycles that pass per second. If you count, for example, let's say 10 crests moving each second, we can say that that frequency is 10 cycles per second. And in honor of Heinrich Hertz, this is who inspired Maxwell's work, who discovered radio waves, a CPS is also called a hertz, which is a very common thing. If you had done anything with radio, you might have heard of the expression. So we've established that light has these two properties, wavelength and frequency. How do they go back to one another? Now, the formula for the relationship that we kind of have already established here can be expressed as follows. For any wave motion, the speed at which a wave moves equal to the frequency times the wavelength. Waves with longer wavelengths have lower frequencies. Mathematically, we can simply say this as C equals lambda F. The Greek letter for L, lambda, is used to denote the wavelength, and C is the scientific symbol for the speed of light. So if we were to rewrite this formula for the wavelength, we can say lambda is equal to C over F. F, of course, if you didn't know, is frequency. Now, this is all good and all, but light has some unusual things about it. And we're going to look at this as a photon. Well, and why do we do this? Well, the electromagnetic model of light that was established in the 19th century was a huge triumph. However, at the beginning of the 20th century, we started getting more sophisticated experiments that reveals light behaves in certain ways that can't be explained by the wave model. So reluctantly, physicists had to accept that sometimes light behaves more like a particle than a wave. And when light takes on something like that, we saw, hey, this is a packet of electromagnetic energy, and so we are going to call this a photon. So light has a dual behavior. The fact that light behaves like a wave in certain experiments and like a particle in others was, at the time, a very surprising and unlikely idea. After all, our common sense says that waves and particles are opposite concepts. A wave is a repeating disturbance that by its very nature is not only in one place but spreads out. A particle is something, however, that can only be in one place at any given time. Now, countless experiments have been done to confirm that electromagnetic radiation can sometimes behave like a wave and at other times behave like a particle. And this, of course, had some confusion because, is it a wave or is it a particle? Well, light has this duality, and in physics, this was eventually resolved by the introduction of much more complicated theories of waves and particles that we refer to as quantum mechanics. That's, of course, something that's going to be well beyond the scope of what we're covering, of course, but the important thing to note is that light does have these properties of both a wave and of a particle. So let's connect these two models. We can use the idea of energy, actually, to connect the photon and the wave models. How much energy a photon has depends on its frequency when you think about it as a wave. A low-energy radio wave has a low frequency as a wave, while high-energy X-ray at your dentist's office is a high-frequency wave. Amongst the colors of visible light, violet light photons have the highest energy, and red light photons have the lowest, again, going back to those frequencies. In the above example, which photon, of course, would have the longer wavelength as a wave, the radio or the X-ray? Well, if we think about it again, radio waves have a lower frequency, so we could say that the wave cycles are longer. Now, the thing you might ask, though, why does light get dim? If it doesn't really lose its properties, right, because it's a particle, why does it seem to get dim? Well, light, by its nature, radiates away from its source. And when it radiates out, it's radiating out in every direction. So it's going to spread out in such a way that the energy per unit area, which is the amount of energy passing through one of the, kind of these small squares that you can see in this diagram here, decreases as the square of the distance from source. We refer to this as the inverse square law for light. For example, if we were to stand twice as far from the source, our eyes will intercept 4 times less light. If we stand 10 times away, we're going to get 100 times less light. So you can really kind of see, especially, again, look at this diagram. You can see, even though we are not having the light change in any particular way, it is spreading out simply just from radiating from the source.